Good morning or good afternoon, everyone. Thank you for joining us. This is Hamish Stewart from the Viavi Solutions EMEA sales team. We still have people joining the webinar, so we're just going to wait a few more minutes before we start, so please bear with us. So thank you for waiting, and for those that have just joined, good morning or good afternoon, depending on where you are, and thank you for joining us. This is Hamish Stewart from the Viavi Solutions EMEA sales team, and I want to thank you for joining our webinar today, which will be on testing FM radios and FSK modems. We have a lot to share with you on this subject, but before we begin, I'd like to let you know a few things about the format that we will be following today. The webinar is being recorded and will be available for you to review or share with your colleagues in approximately 24 to 48 hours. We will send an email to all attendees, which will have a link to the recorded version. All lines are on mute, but we are monitoring the chat window and will try to answer your questions at the end of the webinar. If we're unable to do so, however, we will reach out to you individually to make sure that you get the answers that you seek. And now I'd like to hand over to our speaker today, Barry Hack.
So yes, good morning, good afternoon, everyone. Hopefully today will go okay. I'm sitting in an old farmhouse in a national park in the UK, but with the luxury of cellular communications, I think we're going to be good. So apologies to the guys that have sat through, I think this is my 7th webinar, sat through all of these, but just a few introduction slides. So I'm Barry Hack, I'm the solution engineer for the radio test set products. There's my details, but just including the other guys who are the other solutions and field application engineers. So we have Mohammed in Asia Pac region, and we have Dave, Mike, and Bill in the Americas region. So they're your primary technical contacts. Obviously, anyone in EMEA, you have Hamish, you have Francesco, and you have myself. Very brief history of Viavi, and this is focused on the radio test set side. I started life in Marconi, which then became part of IFR out of Wichita, Kansas, which is basically where the radio test sets are designed and produced today. Then in 2002, we joined Aeroflex, and then in 2014 became part of Cobham, and more recently, 2017, we became part of Viavi Solutions. So we're just one piece of the big Viavi family. Okay, it told me my audio was lost there. I hope it's back now.
Yeah, we can hear you okay now, Barry.
Fantastic. So what are we covering today? This was the, I think the little strap line that was up on the invitations. I'm talking about testing FM radios and applications for FM and FSK modems. Okay, and then testing and programming those radios. So we'll have a quick look at maybe sort of applications for FM radios and FSK modems. We'll talk about key features of the radio test set, and this will come into light as we talk through the different slides. You'll see why some of these features are important. A very brief introduction to FSK modulation and some of the issues you might see there. And then we'll look at automated testing of radios. Just throw in a few extra ideas that you can use a test set for outside of just basic testing. And today I'm going to focus on using the 8800 SX, but you'll see there's a few pictures in there of the 3920B just to show some extra features on that product. And remember that the 3550R is basically the same platform as the 8800SX. So in most cases, those two products will do comparable measurements. So where do we see FM radios and FSK modems used? Well, FM radios have been around for a good time now, many, many years, and they're used by both consumers and commercial users. So you might have simple things like walkie-talkies that you would use if you're going camping with your family. I see walkie-talkies used in my local school for the different classrooms to communicate between each other, between the rooms. You have commercial radio stations, so these are maybe in the FM broadcast band. And you have a lot of professional users, both commercial users, could be shopping malls, could be chemical plant, industrial plant, and also public safety. So, for example, in the UK, even though the emergency services have the Tetra network, airwave network, the fire crews, for example, when they go into a building that's on fire, they tend to switch to FM radios because of the breathing apparatus systems. They're still using FM radios for those systems. So there's a lot of use of FM radios. And for the modems, excuse me, so these are basic FM-based digital modems. Again, commercial users, quite a lot of those. For example, water companies, electricity companies may be using them to monitor and activate things on their networks. Home automation, you'll see a lot of things like, garage door openers, remote light switches. Some of those will use these types of modems, central heating controllers, those types of applications. And there might be paging systems. So in the UK, for example, we have the POCSAG system still, and that's used by people like, part-time fire crews who are in rural areas, the RNLI, the lifeboat people for sea rescue and mountain rescue. So they would be people normally working in another job. Their little pager that's clipped on their belt will ping, will alarm, and they know then just to stop what they're doing and run and get in their vehicle and get to their base because there's an emergency. So there are many, many applications, and these applications have been around generally for a lot of years. So what are the pros and cons of staying with FM radios and FSK modems? So the positives I've put in green and what I think the negatives are in red. So obviously well proven over time. FM radios been around for many, many tens of years. They've improved more and more as we've gone through different generations of radios. They're relatively low cost, simple to make, simple to service. Anyone in a workshop probably knows how to service an FM transceiver these days. Some of the issues, though, might be things like lack of security and encryption, which is becoming increasingly important in the modern world, especially with people having easy access to FM receivers, easy access to SDR radios on USB sticks, $30, 25 euros. You've got quite a powerful receiver these days with lots of free software on the internet. And they're spectrally inefficient compared to the modern digital systems. So again, with digital, you'll get more users in a chunk of spectrum, effectively. Similarly for the modems, again, well proven over time, relatively low cost. But again, they have a lack of security and encryption, at least in their basic form. And this might be important, for example, if you're involved in critical infrastructure, so electricity, gas, oil, water, big industrial plants, chemical plants, oil refineries, those types of things, shipping ports. And we've seen examples around the world where these systems have quite easily been broken and taken down during cyber attacks. So these are some of the issues which are better served these days by the digital radio systems. Okay. Let's just quickly touch on some of the FM transmitter measurements. Again, it's very similar to AM and in some respects digital measurements, obviously with some different measurements in there as well. So for the transmitter, we're going to be interested in looking at things like the output power, excuse me, frequency error of the radio, okay, the deviation of the modulation, the distortion of the modulation, and this could be measured as distortion or SINAD or SNR. We might be interested in the transmit audio bandwidth, although I don't see a lot of people doing that test, but I will cover it on the receive side today. You might want a spectral plot because you can then show that you're within your allocated bandwidth for that channel, or you might be looking for spurious signals or even harmonics. Okay, we can actually do particular harmonic and spurious tests outside of the spectrum plot. And on the receiver side, we'll look at sensitivity. Again, we might look for maybe 12 dB SINAD or 5% distortion would be good examples. We might look at receiver selectivity and bandwidth. How good is my receiver at picking up the signal on my channel without picking up signals on neighboring channels, which we would see as interference, of course. We might want to look at the audio bandwidth, and again, I'll demonstrate that. And then the other tests we might want to do with the radio test is we might want to look at the antenna system, or if we have a coupler system where we've coupled in to an antenna or we're monitoring from a live antenna through a coupler. We might want to do those tests, and we might want to use a tracking generator for checking things like filters and duplexers. So let's look at some of these measurements in a little bit more detail and look at some of the issues we might find. So here's one of the radios I have, and for a particular input level into the microphone, which is a few millivolts of a 1 kilohertz tone, I've keyed the radio and I'm transmitting. So what I'm seeing here is that, you know, I'm happy. My power is down here, and it's green. And you see we have 2 power meters. I'll explain the difference in a moment. But my power's green, everything else is good, and I notice the modulation is red. So for this particular radio, with the level of audio I'm putting into it, I should be seeing 1.5 kilohertz of deviation. So I've deliberately set it to quite a tight specification to show that fail. Okay. Now, is 1.6 kilohertz deviation acceptable? It may be. But again, if you look at this visually very quickly, straight away, I know that is my problem because it's red. Everything else is green. Okay, so that's the first thing I see here. Now, one of the issues you have with FM modulation, which is the same as or similar to what you have with AM depth on an AM radio, if you have noise of multiple tones, you will add their values to the deviation. So if I was, for example, generating 1.5 kilohertz of deviation from my 1 kilohertz tone, but I had another 100 hertz of deviation caused by noise or another tone that I'm using, maybe a subaudible tone that's not filtered out very well, that will add to the measurement. So then you would see the modulation appear to be high. Now, the bad thing with that is then if you come to retune the radio, you tune this back to 1.5 kilohertz, so it passes, but in fact your actual signal deviation is now more like 1.4 kilohertz. So you're now going to under deviate. So you have to be very, very careful with the modulation measurements. And it's a similar argument to what we use for tuning the digital radios. The FM deviation meter has to be very accurate, very flat. But you need to be aware of if you're generating any other tones or noise in the system, because they will be additive to that value. Okay. Just to touch on the 3920B, I can, with that, I have an audio analyzer that I don't have on the 8800. So with that, for example, you can see that I have my 1 kilohertz tone here, and then over on the left side here, I have a 67 hertz subaudible tone. You see that the deviation is lower because the level is lower here, but that's actually showing both my 1 kilohertz test tone and my subaudible tone. So if these were additive, it would push my modulation measurement to be out of spec. So be careful when you do this, and make sure that your AF bandwidth isn't set to none. Make sure that is set to a 1 kilohertz filter or voice filter, or maybe you want to use a 300 hertz filter to actually look at that 67 hertz tone and see what the deviation is on that. Okay. So main thing is here, any signals coming through, their deviations will be additive and will increase that modulation measurement. What I showed you on the last slide was quite interesting because that was after I'd calibrated the 2 power meters. So you'll notice on the all these test sets that we have 2 power meters. We have an RSSI meter, which is actually a DSP signal, digital signal processing power meter. So that is good for all types of signals, really. So that will give you good power. Doesn't matter if it's if we're running AM, FM, or a digital system. That will give you a very accurate power measurement. However, the actual RF power average meter is a classic, diode and capacitor based, shall we say, analog meter, and that is actually more accurate for signals with constant amplitude. So, for example, things like FM, things like constant amplitude digital systems. So P25 would be such a system in the US. So the actual RF power average meter will give you slightly better accuracy than the RSSI meter, but its limitation is it doesn't particularly like any signals that are either bursted or have varying amplitude. Okay, this will be brought up more in the next seminar in 2 weeks' time when we talk more about the power meters. So what you see in this first picture here, this was my test set before I calibrated it. Again, you see my modulation still failing here. Everything else is about the same. But what you notice here is my RF power average meter is reading about 4 watts, but my RSSI meter is reading 4.3 watts. So there's quite a difference there. So we have these 2 buttons. So the RF power meter, we can zero the meter, okay, and the RSSI meter we can normalize. So the zero, just you press that and it will say zeroing and it finishes. It takes just a couple of seconds. It's okay, so that's uncalibrated. Okay, so we push these buttons. So I've done the zero on the power meter, on the RF power meter. I'm now going to normalize the RSSI meter. So you'll get this screen come up saying normalizing for some seconds, and then it'll tell you it's finished. Okay, successfully. Now a good thing to check is these 2 values here for the TR and the antenna port. Typically these are somewhere around less than plus or minus, say 1.5. If you get values of 100 or some other big number, that could be indicative of an issue with the test set, or that you actually have some signal still connected to one of the ports. And that signal may purely be you have an antenna connected and it's receiving some signals off air, and you haven't thought about that. So be careful when you do those zero and normalized measurements that nothing is connected to any of the RF ports. And then if we look afterwards, you now see, okay, so this was reading about 4 watts. Now it's reading 3.72, and this was reading 4.3 watts. It now reads 3.7. So you can see now these values are remarkably similar after calibration, okay? So always make sure that you've zeroed and normalized your power meters when you're taking power measurements. If we look at harmonics and spurious, I'm showing effectively the same thing I showed last week for AM measurements. I can, on the 3920B, I can set up a harmonic and spurious search system. So my start and stop frequencies and my thresholds for passing and failing. Okay, I key the radio, tell it to do the harmonic and spurious check, and both of my harmonics are good, and I have no spurious above my minus 50 dBm threshold here. So it's not failed on any spurious signals. If you want to do this on the 8800SX or the 3550R, it's a manual test. You'd have to use the spectrum analyzer, or you'd use maybe the receiver and look in maybe a 25 kilohertz channel and switch between those frequencies. But the spurious search, you would have to do that manually on the spectrum analyzer. If we look at receiver sensitivity, classic, everybody's done this. Okay, so I always start with, so I've got a UHF radio here. I will start with a high level. I'm a dBm guy. I was an RF design engineer, so I use dBm. But if you click on the units, you can have microvolts or dB microvolts, depending on how your radio is specified. Okay, so level units here can be changed while we're at it. In fact, I'm showing dBm here in watts. These could both be in watts if that's what I wanted. Okay, or dB watts. You have a choice of units. But I'm generating a signal. I have some modulation. So I have a 1 kilohertz tone, but 2.5 kilohertz of deviation. I'm feeding that into my receiver, and I've got very good distortion, and I've got very good synad measurement. Okay. So we now really want to do sensitivity measurement. So one way might be that you're told to change the level, and in this case, I've been told to set it to minus 121 dBm, and I have to check my synad is over is bigger than 12 dBs, and my distortion is less than 10%. Okay, so again, both of these values are what I expect. Now, quite often, if you're connected to a radio into the test set audio input, you've also got the audio level here. So a lot of the times, I think people will tell you, or the manual will tell you to set the volume maybe to halfway. So you can verify that is halfway by just checking that, putting a test limit on that audio level that we receive here. If it's too low, of course, if it's very, very low and we're picking it up with noise, we could potentially fail the synad and distortion, even though we have a good radio, purely because the level has been turned right down on the radio. You turn the level all the way up, you may get some audio distortion out of your radio. And again, these measurements could fail. So it is always good to check that the audio level is in an acceptable range. Not too low, not too high. On the third one here, I've actually added cable loss. So all these measurements I've done so far, I didn't put in any cable loss. Now I've added cable loss. And on the generator side, half a dB doesn't make a lot of difference, but on the analyzer side, my 3.7 watts that I measured could really be, say, 4 watts. So it is much more significant when you're looking at numbers of watts than it probably is when you're looking at trying to get sensitivity down to the nearest dB or the nearest microvolt. So bear that in mind. On both the generator, we can set a cable loss or cable gain. And similarly, if we expand the receiver with this blue button, we have a similar measurement like this on the receiver side. Another measurement we might want to do is some form of receiver selectivity. So in this case, my radio is set to 144 megahertz. So I've switched to a different FM radio now. Now I know I've got about minus 36 hertz error in that frequency, because when I key the transmitter, it tells me I'm out by minus 36 hertz. So I'm just going to put that in there for us to think about for a moment. What I'm then told to do in my service manual is I've got to reduce the frequency, the RF frequency, until I drop below 12 dB SINAD, or around 12 dBs. So you can see that's what I've done here, and it's fluctuating around about 12 dBs, and I record this number. So I can punch in a number here, just as a numerical number, or when you touch on this field to add that value, there's a little sort of curly arrow on the right hand bottom corner of that screen. And if you click on that, it expands to this screen. So now I can move along my scale, so I can change my resolution and then use my up and down arrow keys. Or I have a little thumb wheel that I can move with my finger because it's a touch screen. So I can scoot around values using the thumb wheel. In my case, I like to use the up and down arrow keys and then change the resolution here, up or down, to get the value that I'm looking for. Okay. So I've done that, got my 12 dB SINAD value. I've then done the same thing on the high side. I've gone up in frequency until I've gone down to well, it's just about to fail on my 12 dB point, and that's my two values. If I take those two values here, what it tells me for my radio is my total bandwidth is the difference, 12.7 kilohertz. But based on the center, my percentage of non-symmetry is 35%. So what it's telling me is that it's not centered around my center frequency. Okay, so 35% is quite a big value. So my actual channel is offset from the center. If you remember, we had a 36 hertz error up here. But if we go to 36 hertz, we're down in the these last two digits here, which are not so relevant. I'm only really looking at 4 digits. So that 36 hertz is not really impacting this measurement, but I still have this really big amount of non-symmetry, and that's quite important. The radio last week was an AM radio, and that had about 25% non-symmetry. This is an FM radio. This is one that would be used typically by radio hams, rather than the more professional users. Not many radio hams aren't professional, but this particular radio is a radio ham. It's a quality radio from a well-known manufacturer, and it has that amount of non-symmetry in the channel. The one I used last week, the AM radio, is used at airports, 25% non-symmetry. So this is a nice little test for you to do, just to have a look at the front end filter on those receivers. And like I say, a lot of people do not do this test as standard, but it is quite interesting how big those numbers can become. So it might be something you want to check on a couple of your radios. Switching to the 3920B, excuse me, you can actually put in, it lets you start at the center, and it puts a frequency here. It lets you go down to the low value and touch a soft key, and it automatically fills this field in. Then find the high value, and it automatically fills that field in, and it will then tell you the bandwidth and the percent non-symmetry. So this is actually the radio, the AM radio last week. Okay, so that was a 25 kilohertz channel. It's a little bit low, and it had 24%. If I just jump back to this one, this is a 12.5 kilohertz channel. So we're actually, the channel is, at least in this form of measurement, I'm looking at 12 dB SINAD, that's actually too wide, and that non-symmetry is significantly worse than the other radio that I showed here. If we want to look at audio bandwidth, and this is on the receive side, so this is, obviously we want the voice to go through the radio, and a lot of time we use, for our measurements, if we're looking at 1 kilohertz, we'll use a 300 hertz to 3.4 kilohertz bandpass filter. That takes out any high-end noise, but it also takes out any low-end noise, which could be sort of rumble or main sum or subaudible tones. more modern filters, you have things like the CCITT and C message filters, which we also support. But we might want to actually sweep the audio and see how the audio behaves in the channel. So of course, the audio that I'm putting out is very well specified, very flat. But let's see what the radio does with that. So I would expect a voice channel, like I say, is typically 300 hertz to 3.4 kilohertz. So what I might start with is I have a 1 kilohertz tone and I measure the audio level. So here I've measured 47 millivolts. Okay, and I could change those units to millivolts if I wanted to. What I've done then, my service manual tells me to find the lower and upper audio frequencies that give me half the reference voltage. Okay. Now I've kept it as voltage, so I've said, well, that's about 50 millivolts. So I'm looking for something about 25 millivolts, and that's what I've done here for my lower and upper audio frequencies. Something else you could do on this first plot, once you have your 1 kilohertz reference level, you can change the units from volts to dBr, so relative. So I could actually do this as a dBr, relative dB measurement if I wanted to, and then look maybe for 3 dBs or 6 dB degradation in that level. Okay, I've kept it simple. I've just left it as volts. So I found the two values that give me half the voltage. And on this radio, again, this is the amateur radio. I'm measuring about 170 hertz for the bottom end and 2.2 kilohertz for the top end. So that's nothing like what I would normally expect for a voice channel. Will it let voice through? Absolutely. But you may lose a bit of clarity because you don't have the slightly higher tones here. So again, that's something you might want to check occasionally on a radio, just to see how the audio bandwidth is behaving. To do something similar on the transmit side, exactly the same. You transmit, 1 kilohertz modulation tone, and then just sweep that modulation tone, sweep it down, sweep it up, and again look at the audio that you receive on your demodulated signal on the radio test set. Let's have a quick look at FSK modems. So really, very basically, FSK modems or modulation, it uses FM, but rather than we are modulating the signal with, we're modulating the frequency with the voice. So effectively, as I speak, or if it's music, I'm singing, or whatever I'm doing, the frequency is directly modulated in sympathy with that voice or music. Okay, so it's a direct modulation of the message you're trying to convey, or the data you're conveying, which is the voice, for example. With FSK, what we do with that is still FM, but effectively we have discrete frequency offsets to represent the digital data bits. Usually those transitions are filtered. Why? Because it improves spectral, shall we say, channelization. If you don't filter it, anything you don't filter quickly, so anything you don't filter and it changes quickly, will cause spectral spreading and interference in neighboring channels. So normally you would filter things. You would filter that modulation. So rather than jumping directly to the points, it will move smoothly between them. And I'll show you some examples in a moment. Okay. Now, one form of FSK or frequency shift keying is MSK, minimum shift keying, and that's a special version of FSK where the deviations and the data rate are linked to give you a value of 0.5, and basically it minimizes the adjacent channel interference, shall we say, by nulling out that point on the modulation. If you apply a Gaussian filter to that and get GMSK, well, that's the same modulation that we would use, for example, in the original GSM cell phones. If we look at 2FSK, one example there is POCSAG. So here's POCSAG. So with this, you see the frequency is literally banging from plus 4.5 kilohertz to minus 4.5 kilohertz. So if I was to look at this, I would say maybe this is a 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1. So I can recover my digital data because it's one data bit, and each clock cycle is it plus 4.5 kilohertz or minus 4.5 kilohertz. That tells me if it's a 1 or a 0. Okay, but there's no filtering on that. It's literally just banging between the two frequencies. If I look at, for example, 4 FSK, DMR, so again, this is just using the FM meter. This is not using a digital demodulation scheme. You can see this is moving around, but you probably see it's filtered. Now, actually, for these DMR and XDN DPMR systems, there are only 4 frequency points that we use. But here you can see the frequency is all over the place. You might see one of the levels looks to be about here, but sometimes it's bigger. You know, one of the levels seems to be down here, another level's here. Okay, so you'll see different levels, but depending on what data came before, there can be some overshoot or some undershoot because of the filtering. But that's all taken out in the receive side, so we can recover those 4 positions and still get our 2 bits of digital data. Okay. 2 FSK, we're sending 1 bit, it's a 1 or a 0. 4 FSK, we send 2 bits. We have 4 positions, 2 bits of data. You might notice occasionally you get something like this. You have a little flat spot here, okay, which I think is going to be about 600 hertz for DMR. And that's actually going to be useful, for example, for clock synchronization and timing. So we can actually tune our receiver to the transmitter to help optimize the performance. And then there's C4FM, which is another flavor, shall we say, 4FSK, which P25 uses. Okay, sort of looks broadly similar to DMR. The deviation is a little bit different, but it's interesting that these modulations, you can see quite a lot of information about them purely using an FM receiver. Okay, can I decode them easily? No. Can I check their absolute accuracy in terms of the digital performance? No, but I can get some information. Now, when you've got these FSK systems running, and I'm going to pick on POCSAG as a simple example. Okay, this is going between 1s and 0s. But what I might want to do when I have a POCSAG transmitter is I want to calibrate it. So I'd have some sort of calibration meter. I have another FSK modem, which is used by one of the UK water companies. And again, that's exactly the same thing, but that has a 100 hertz tone, and I'll show you that later. But this is POCSAG, and I have a POCSAG transmitter, okay, and I should be checking this is working. So it should be a 1 kilohertz test tone, and I'm trying to get plus or minus 4.5 kilohertz of deviation. So great, I've got a 1 kilohertz tone. So even though it's effectively a square wave, I'm still getting the frequency here in the AF counter. Okay. But my modulation is good. This is 4.5 kilohertz here, roughly. So I'm happy with that. And my frequency is good. Okay. But if I go and look at the picture on the oscilloscope on the DMOD, I think, well, actually, this doesn't look like it's plus or minus 4.5. It looks more like plus or minus 4.2 kilohertz. Okay. So why is my meter reading 4.5? Well, if you actually look at the signal, if you were to zoom in on this, you'll actually see it. There's a little bit of overshoot, and then there's some ripple in here. Okay. So this is caused by the baseband in the POCSAG transmitter. And because that baseband is overshooting, remember I said that the FM deviation meter is a peak meter, peak reading meter. So it's actually found that peak, which is 4.5, and that's what it's given me here. Absolutely correct. So be very careful, especially with these FSK systems. If you're trying to do calibration, be very careful. If there's any overshoot or ripple, what you're going to see here is a peak value. Okay. So even though I think I've tuned my POCSAG generator for 4.5 kilohertz deviation, I haven't. Okay, I really need to look over here and probably try and do a visual inspection look at the center line here and make that more like 4.5 kilohertz. Okay, so that's one of the things that will catch you out when you're calibrating FSK modems. So let's look at a professional modem. So this is used by a water company. Okay, so they're using it really for, you know, data logging, telemetry, remote switching. So they're switching water valves, they're switching water pumps. They might switch chemical cleaning systems into, you know, solutions into the water in a water treatment plant. Those types of things. Could be similar. Electricity company might do the same thing, but switching different circuit breakers, switching different routes for power cables if there's a fault on a cable. And of course, they're also monitoring. So if they see a fault at on a particular power line, that can be reported back to the control center. So none of these are high data rate. They're doing quite simple things with them. But remember as well, these modems have very little protection on them in terms of security these days and encryption. So you can employ encryption, of course, because it's digital. But they are quite easy to break into. And you see a lot of security issues now. And we've seen this maybe in Eastern Europe and around other parts of that side of Europe, shall we say, without talking too much about particular countries, where they've had systems taken down, national systems. So maybe a whole nation has had the electricity cut. We've seen similar examples in the US. They won't tell us it's anything to do with a potential cyber attack. It's always a fault in the system. But I don't think you take down one side of your country by having a fault in part of your system. So be careful again with some of these modems in terms of security. But for this particular modem, the calibration is plus or minus 2 kilohertz deviation with a 50 hertz square wave. So what I've actually done, I've actually digitized that RF signal. So I've actually recorded it, and then I've mathematically regenerated it from the recording. So there's my signal. Okay, looks good, I guess. So one cycle, so an up and down on the square wave is 20 milliseconds. Great, that's 50 hertz. That's fine. But what does it show me? Well, it's not a square wave. Okay, so you see it starts a little bit high and it droops. Okay, now it may droop because that's a feature of the radio hardware. It may droop down, droop down in power because, in deviation because of something happening in the radio. Okay, but remember, if I look at this on an FM deviation meter, what am I going to see? I'm going to see 2.03 kilohertz. Great, I've calibrated my radio. No, I haven't. I've calibrated it to the peak value. Okay, so it tells me I've got a 2 kilohertz deviation, which I haven't. Actually, what I've got, assuming it's a frequency offset in the system, a frequency error, I've got a 1.77 kilohertz deviation with a 230 hertz offset or frequency error. And that in itself is not always true. Sometimes the offset is actually caused by the radio modulator. Just like you saw with the receiver bandwidth, you saw that there was the symmetry was out by 24% or 35%. Again, you could have symmetry problems with the modulation generator in the modem. So be very careful again when you're trying to tune these modems, because typically if there's some sort of offset or if there's a peak like at the start here, or there's a little bit of overshoot at the start, your FM deviation meter will read that peak, not your average level. So you need to be careful. I'll finish up this. I apologize to anyone who was here last week. These are exactly the same slides, the last few. But I've used the 3920B, again, just because I've grabbed these from last week. They're quite nice pictures. The first one, I might want to do a wideband sweep of an antenna or an antenna system in terms of power. So in this case, what I've done, I could use a VSWR bridge and do a VSWR sweep, but what I've done here, I've got a golden antenna and the antenna I want to test. So 2 antennas the same, and I've just done a wideband sweep, okay, and said, okay, so I'm probably interested in this range, which is exactly right. It's a VHF antenna, so it should give me best signal throughput, shall we say, in the VHF band. Then what I've done here, I've zoomed in, and I've done a recording with 2 known good antennas, so 2 golden antennas. I've saved that on the test set, and then I've recalled it, and that's my green trace. I've then kept 1 golden antenna on one of the ports, and I've put my antenna under test on the other port. And now you can see a difference. Okay. And I've just used the generator and the antenna port, so they're physically, what are they, 5 centimeters apart? So they're very close. You don't do this if the antennas are a long way apart. Do not put your hand between the antennas. You'll impact the measurement if you put anything near them. But you can see that that antenna is broadly following the same pattern. It's very close. So I would say, okay, this is also a good antenna. So it's a very, very quick way to check antennas, especially if you've got just screw-on antennas on your portables. You can very quickly put 1 golden antenna on there, and then put you may have 100 radios. Just put all the antennas, one at a time, onto the test set. Do I get a trace like this? Yes. It's probably a good antenna. Do I get a trace that looks very different? Yes. It's probably a bad antenna. Okay, so it's a quick antenna check, if that's what you want to do. And we can also use that capability on the tracking generator to find a notch or set or tune a notch on a filter. We might have duplexers, diplexers, whatever we're using. We can sweep the frequency and tune those devices. We have very good dynamic range that lets you do that tuning, and you can even zoom in on the spectrum if you're looking for a very, very deep notch. You know, maybe minus 90 dBc, you'll be able to tune that out using the tracking generator capability. You can do similar things on the 8800SX and the 3550R, okay, but I just chose to show this on the 3920. There is a previous webinar talking about these types of functions in more detail, okay, in this series of webinars. So that one's already available as a recording. And the things I've talked about so far are what we classically think of doing with a radio test set. Let's test a transmitter, let's test a receiver, let's tune a transmitter, let's sweep the cable, let's sweep the antenna and do some checks on those. That's what I call classical use of a radio test set. But think about something. Think about maybe some automation of the radio. Think about, is annual maintenance enough? You know, most people will sell, 1,000 radios to a chemical plant, and there'll be annual maintenance. You'll either go to the plant or they'll send the radios in and cycle them, each month, some of the radios, and you'll do annual maintenance. Sometimes that's not good enough, especially if the radios are older and they're starting to drift. You might want to do that more frequently, especially if you're in a critical environment. If the radio test set's sitting there, and some of these companies have their own radio workshop just to support their own company, why not use those radio test sets? So when you're not testing radios, just use them to monitor, even off air. Monitor the transmitters. Are the radios that are transmitting on frequency? Is the power dropping because the amplifier's been stressed and got hot over years and it's lost a bit of gain? Is the modulation out of spec? Receiver sensitivity, a bit more difficult to do reliably off air, but you could do some basic checks, and you can also use it for interference hunting or monitoring on your channels. So don't wait until your government agency calls you to say you're outside your frequency limits because your radios have drifted, or you've got some nasty harmonics or spurious because your power amplifier's gone a little bit bad. And don't wait for your users to lose comms and come screaming, hey, my radios don't work. Use those test sets when they're not being used to test radios. You've paid a lot of money for them. keep them in use and just monitor things off there, and just automate that. So it just sits there doing some measurements for you. Finally, I'll touch on a little bit of remote control and test scripts. So if you're, for example, a radio workshop, you could be a single user working from home, but if you're a radio workshop, you've got lots of users, lots of test sets, many different radio types, you might want to automate some of that testing. Okay. If you've got the same radio types, but you're doing a lot of them, you probably want to automate. Anything that's high volume or repetitive, just think about a little bit of automation. Okay. What takes a lot of manual button pushing? You know, if you're doing sensitivity tests where, like my radio, it said set the level to minus 121 dBm, is it better than 12 dBs? SINAD. That's great. But if you have a different radio and it says lower the power level until you get to 12 dB SINAD, now it's going to take you a lot of time because you're having to manually lower that level. You know, you're turning a wheel, you're dialing in numbers, you're pushing up and down arrow keys, whatever. Okay, that's the type of test you want to think about automating. Receiver selectivity, I showed you that. That's another test. The audio bandwidth, that would be another one. All these measurements where you've got to tune down to find something and tune up to find something. Think about automating those ones, the ones that take a lot of manual operation, which means a lot of time. Okay. And as I said on that last slide about monitoring your channels and interference hunting, have a little program that just maybe looks at the spectrum, does a peak search, and if something's on a channel that you expect to be clear, it's probably someone who shouldn't be there. We see a lot of people having issues where both analog and digital radios where people are jumping onto their repeaters. So an illegal user or transmitter, which is going through someone's private repeater, so they can bounce signals around different areas or different parts of a country. So, you know, you'd be able to pick those signals up, and then maybe with a directional antenna start to find roughly their location. Or if you pick those signals up, you know, call up your government radio agency, say, hey, I've got a problem with my, you know, I'm paying you guys money for my license, and there's some idiot using my channel. Can you come and find them and, you know, take them away, please? So sometimes you want to get a little bit of evidence. Sometimes it's for your own use, so you can have an alert and start fixing a problem before your users see it becoming a real problem. Okay, so it's preemptive maintenance, shall we say. Some of that you can do yourself. I'll show you that in a moment. Other ways you can do it is test scripts on the test sets. So 3920 is probably the best example. We have scripts already written on 8800 as well. Unfortunately, there is no script capability on the 3550R. So 3920, we can have it built in, and you can actually write your own scripts built in on the test set if you want to. 8800, we're the only people, Viavi, the only people that write the scripts internal to the unit. But you can do your own scripts using remote commands, using Python, C#, LabVIEW, and other programs. Okay. So another thing you might want to do is to show your instrument on a remote desktop. So we use Type VNC, for example. We can remote into the equipment. So it can be local, it can be somewhere in our intranet, it can be in another part of the world. And we can show that equipment. It's bidirectional, so you play on the laptop or the computer, it changes on the test set. Or if someone changes it on the test set, you'll see it change on your remote desktop. So that's a very simple, should we say, manual remote control. You could use Python to write a program, and apologies, this is an AM radio from last week, but it shows a very good example. I could very easily turn these AM measurements to FM and do an FM radio. Okay, so again, I can show measurements very quickly, and to do one channel of my radio, that took 20 seconds for all my transmitter and receiver measurements. Okay, you'd be hard pushed to do that in a manual test. And if you've got multiple channels, you see how that time becomes quite important. Here's another one. This one's actually written inside the 3920. So this is a script I did that controls both the radio itself via the USB port on the 3920 and the test set. I've had to hide some of the things here because it's a customer's particular radio. But that took 28 seconds to set up the radio, read out all its parameters about its software, even the power amplifier temperature. I've got that reading out of the radio. And then I do one channel here. That took 28 seconds. That's setup plus one channel transmit receive measurements. Again, you have multiple channels. You see how this becomes very, very effective. Okay. And I've also done that external as an 8800 application. Okay, if you're still using your old test sets, that's great. You know, I'm a Marconi boy. I've gone through IFR, Aeroflex, Stabilox, Wiltec. That's all part of our division as well. I've named a couple of others there, but any of these old test sets are getting old. They're getting hard to repair. Calibrating them once a year these days is not viable in some cases because they're drifting so much. You need to be careful. They're sort of okay for FM because you're only using a 1 kilohertz tone, but please don't use them to tune your digital radios. And you tune digital radios using FM. But your deviation meters have a lot of uncertainty compared to these modern test sets. So that's going to impact both FM and digital radios. Okay. Obviously, we have the best test sets. The FM deviation meters are very, very good, and they're optimized for both analog and digital. So to finish, FM radios, FSK modems, been around for many years. People still get caught out on some of the measurements. They don't think about the deviation meter being a peak meter, for example. Any noise or additional tones, you know, even subaudible tones, can affect and impact that reading. So you fail a good radio, or you tune a good radio and make it bad. Okay, make sure the measurements are good. So the radio test set has to have good system noise. Okay, some of the old ones actually add their own internal noise, which impacts your measurement significantly. Okay, to make use of those spectrum analyzer and tracking generator functions. Okay, and think about automation to save time, effort, and money. Okay, sorry, there's only 2 minutes left, but I'm hopefully throw back to Hamish for a couple of questions now. Thanks for listening.
Yeah, thank you for that, Barry. We do have several questions from the audience, probably too many to get through in the time we have left, but we'll try and get a couple of them answered. So the first question that we have is, can I use FM measurements on my old radio test set to measure my digital radios, or do I need a new digital tester for that?
Yeah, you saw on one of the slides I showed a picture of POC-SAG and DMR and P25 as digital or FSK systems. So you can do some very, very basic measurements, but the problem with the FM meters and modulation measurements and you know, error and everything, you won't get accurate measurements because the FM analyzers don't really like those types of signals. Because they're not behaving as it would expect to see, which would be typically a 1 kilohertz tone. So remember, FM meters typically, except on these new digital test sets, they're optimized for 1 kilohertz and nothing else. Yeah, they work okay in the audio band, but they're not optimized outside of a kilohertz.
Okay.
Yeah.
So I'm getting flashed at here by the webinar system. I think we'll try and get one more question in. Can I use an FM receiver to hunt for interference in a system?
Yes, you can. I mean, obviously, you've seen those measurements again. You could look at the spectrum, and the shape of the spectrum will give you an idea of what the interference is. You could see if the interference is drifting in and out of the channel, or if it only comes on at, you know, like midnight until 1 minute past midnight. So you can get some intelligence on that interference just by using a spectrum analyzer. You could then use the FM demod to physically look at the demod on the oscilloscope and get some ideas. And in fact, If you then take that DMOD and pass it out to the speaker that's in the test set and listen to it, you'll actually hear different things. So you might hear, if it's an analog signal, you might hear the voice. If it's an analog tone, you'll hear or a tone. But if it's digital, you might hear something like or so you'll actually hear different types of sounds out of just out of a basic FM receiver. And that will actually, once you get used to it, that will actually give you an intelligent way of saying, okay, I've got interference and it's a DMR radio. I've got interference and it's a P25 radio. I've got interference and it's a GSM phone. So you can actually pick out some interference types just by listening to the demodulated audio. Okay.
Okay. Well, that's great. Well, thanks again, Barry, and thanks to everyone for joining the webinar today. Unfortunately, we don't have time left in the session to go through and answer the several other questions that we had, but we will answer those via email, and we will send those out to the people that asked them and send them out as part of the webinar follow-up. So if you do have any more questions or would like further information, please reach out to Barry, myself, Francesco, your local channel partners, and please join us for our next webinar in the radio test webinar series. That will be on the subject of internal and external power measurements using the Bird 5017D power sensor, and that's being run on Wednesday, 2nd of September. So with that, I would like to thank you all again today for attending and wish you a good day. Bye.
Thank you, everyone.